All right, everybody, welcome back. My name is Mr. B, and today what we're going to do is we are going to factor polynomials using the difference of squares pattern. So for the most part, this is one of our more simpler patterns, and the big indicator for us is we end up with two values in a binomial. So that's kind of what makes it a binomial, right? There are two things here, and each one is going to be a perfect square. So we say that x squared is a perfect square because it is x to the second power, and 1 is a perfect square because 1 squared is 1. All right, so how the pattern works is we have, technically it looks like this, a squared minus b squared. So if you notice you've got one perfect square minus another, you can rewrite it as a plus b times a minus b. So really the key is understanding and finding out what value to the second power gives you your initial for both values in the binomial. So in this case, we kind of recognized already that x squared is kind of like our a value, it is, and 1 is our b value. So all we really have to do is take the equation and plug in our a's, which are now x's, and our b's are now 1's. So we have x plus 1 times x minus 1. Either one, it doesn't really matter which one comes first, either the minus 1 or the plus 1, because when you're multiplying, those values can switch places and you'll end up with the same thing. It is the commutative property. All right, so this is basically how it works, but one of the nice things about this is we can also actually use our box method as well. So we put our first value here, and then our last value at the end. And then our two diagonals here are going to need to add to our middle value. Well, technically, our middle value here is 0x. So we need two values that are going to cancel each other out. So what we can do is, let me see if I can erase that for us. What I can do is start to kind of factor this. So I need two values that are going to multiply to give us x squared. And I'm going to split that up into x and x. Luckily, the only factors of 1 are 1 and 1. Okay, so when we multiply in x times x, which is like the length times the width here, gives us the area of x squared. And then when we start filling in, we've got a 1x here because x times 1, which is our length and our width of that box at the bottom, gives us a 1x. And kind of the same thing over here. We get x, right? That's the length over here, and the width is 1. So x and 1 is 1x. Now, this only works if our diagonals are going to add to that middle term, which is 0. So that means one of these is going to have to be negative, and it doesn't really matter which one we make. But this way, these two values will cancel each other out, and positive 1 times negative 1 gives us a negative 1 at the bottom. So therefore, our two factors are x plus 1, right, because this is a positive 1. And then we have x minus 1 from the top. So the good thing is we can use the formula on the side here, but if you can't remember it and you are more familiar with the box method of factoring, that totally works as well. All right, so let's take a look at another example here. All right, so this one's a little bit different because we now have a leading coefficient that is not 1. So we kind of need to think about this a little bit differently. Our idea is still to think about, well, we've got two terms here. So actually what we should do is try to see if we can divide out any common terms. First, look for a GCF. There's nothing that multiplies into these two values, so that GCF is off the table. Because we have two terms, we know that we are going to use the difference of squares pattern or the sum and difference of cubes. Well, hopefully we recognize that 4 is kind of the dead giveaway here. 4 is a perfect square. 4 is the same thing as 2 squared, but we can't forget that there's an n squared in this, so we need an n there as well. Minus our other value. Well, how can 1 be written as a square? Well, it is 1 squared. So we have our a and our b values. We have our a squared minus b squared. And that's going to leave us with a plus b times a minus b as our two factors. So our a value is 2n, our b value is 1. And again, it works. Like I said, if we wanted to, we can go ahead and do our box method as well. We've got a 4n squared and a negative 1. And our diagonals need to add to the middle term, which again technically is a 0n. The difficult or more challenging part about this is technically we could have a 4n and an n here. Well, if that were to be the case, we'd have to fill in from there, and we'd get a 1 and a 1 here, right, because those are the only factors of 1. We'd have 4n and n, and no matter if we made this a negative or this one, either way, our diagonals would not cancel. The only way they cancel is if those values on the outside are the same. So when we multiply in, we have a 2n here, right, because 2n times 1 gives us this box down here. And then 2n times 1 up here gives us that area, which is also a 2n. So the way they cancel each other out is if 1 is negative, and that means the value on the outside needs to be negative. And then it works because -1 and 1 multiplies to -1. So there are our two factors, and we are good to go. The last one we're going to do today is a little bit different. So sometimes it throws us off when we've got our variables in the second part of the binomial, but it really shouldn't. It doesn't change anything that we're doing except the number, the constant, comes first, and then the value with the variable is going to come second. So same idea. We look at this and we try to decide if there's anything we can divide out, and there isn't. Nothing multiplies into 1 and 9b to the second. Hopefully, it's a big indicator that 9 is a perfect square, and there are two terms, so we should use our difference of squares pattern. So I need to rewrite this where each of these values are written as squares. Well, 1 squared is 1, and then 3b squared gives us our 9b squared up top. So we have our a and our b, a squared minus b squared, gives us our pattern a plus b times a minus b. We can just plug in from there, 1 plus 3b, and then 1 minus 3b. And that is our answer, because again, these do not factor further. All right, whenever we're factoring, don't forget that at the end, you got to make sure your factors can't be factored again. Just to show you, because we didn't do this in the beginning, if you multiply this out, we FOIL those two binomials, we end up with the middle terms canceling. 1 minus, that should be a minus 9b squared, which it does, and that gives us what we had originally. So we never really want to multiply out when factoring. Factoring is breaking up into pieces, but the idea is if we did multiply out, we should end up with what we started, and again, we do. So what I kind of now realize is, unfortunately, all of our values have included 1s, and part of the reason is it's easiest to do with 1. 1 is a small perfect square, but we really could do it with anything. We could have done a 36 minus 9b squared here. Again, perfect square, and we're subtracting, so it is a difference. So I'd write this as squares, which is 6 squared and minus 3b squared. And then we can just plug right back into that formula. Or again, our box method works perfectly fine here as well. This time my 36 is going to go up top. My negative 9b squared goes in the bottom. 36 has multiple factors, so that makes it a little bit difficult. But we need to remember that these two need to cancel each other out, so they need to be the same. The only way that works is if our values on the outside of our 36 are the same, and the values on the outside of our 9b squared are the same. We get 18b and 18b, and again, one of them is going to have to be negative. So therefore, our two diagonals cancel, and the answer to this one would be 6 plus 3b, and then 6 minus 3b. But the first step when factoring should always be to divide out a common term. What multiplies into 36 and 9b squared? Well, the answer is 9, and we can kind of see that here. When factoring, we got to check to see if anything can be simplified out. So looking at the first binomial, is there anything that multiplies into 6 and 3b? Well, our answer is 3. So I can divide out a 3 from each of these. 6 divided by 3 is 2. 3b divided by 3 is just b. And I can actually do the same thing over here on the side, so we end up with 3 and 2 minus b. Because we are multiplying this, this, and this, the order doesn't matter, and I could rewrite it as 3 times 3 times 2 plus b times 2 minus b, or 9 times 2 plus b times 2 minus b. And that is actually going to be our answer here. Now, I would have saved myself a bunch of trouble if at the beginning I factored out that 9, and then I did the difference of squares here. We're dealing with smaller values and even then a coefficient of 1, which would make this much simpler. But if we didn't, it's okay. We could always do it at the end as well as we did here. But that's another reason why the first step in factoring should always be to divide out any common terms. Okay? If you have any questions, please feel free to leave a comment below. As always, like and subscribe, and thank you for joining us today.